Next, let's discuss how we get a topology out of a metric. Definition 5.2. Let XD be a metric space. And for a point x in x and a number epsilon greater than 0, define the open ball of radius epsilon centered at x to be, well, this is a symbol for it, and it's just a set of all points y and x that are a distance less than epsilon from x. Okay, same sort of definition we made for Euclidean spaces Rn earlier. And again, similarly, define the closed ball of radius epsilon centered at x to be the same notation with a bar over the b, and the less than sign is changed to less than or equals to. So we are allowing points y and x that are exactly epsilon away from x as well. Okay, and then again, like for Euclidean spaces, we will say that the topology generated by the basis of open balls in the metric space is called the topology induced by that metric D, and is referred to as a metric topology, a topology that comes from a metric. So here's sort of a classic example of a metric, although pretty different from the standard metric that you've seen for Rn. Let x be a non-empty set. Define the metric on x times x by distance from x to y is 0 if x and y are the same, and 1 if x and y are different. Only two possibilities. Show that this is a metric and determine the topology on x induced by D. Okay, well, remember the first property is that the distance from x to y has to always be greater than or equal to 0, and that's certainly true. And it has to equal 0 if and only if x equals y, and that again is true by definition. So we can move on to part 2. Distance from x to y, which is this by definition. Distance from y to x would be same thing, just switching the x's and the y's. But x equals y if and only if y equals x, and the same thing for not equal to. So basically the fact that equality is an equivalence relation and is symmetric implies that this metric is symmetric as well. And okay, third property, suppose, okay, so we're trying to prove the triangle inequality. Suppose it's not true. Suppose that we have x, y, and z such that the sum of two sides of the triangle is less than the third. And, well, how could that happen, right? Each of these numbers has to be either 0 or 1. So the only way this left side could be less than the right side is if the two things on the left side are both 0, and the thing on the right side is 1. Okay? But what does that mean, right? If the distance between 2 points is 0, we know they have to be equal to one another, so x equals y and y equals z. And the distance is 1, we know they're not equal. But look, equality is transitive, right? If x equals y and y equals z, then x has to equal z. So we have a contradiction. Okay? So in fact, the left side here must be greater than or equal to the right side. And the triangle inequality holds. Okay, and now they want to know what topology this is. Is it something that we recognize? And in fact it is. So we can, okay, this is topology has a basis of all the open balls, right? So think about the open balls of radius 1 about any point x in this set x. It consists of all the points in x that are a distance less than 1 away from x. Now if they're distance less than 1, then they actually have to be a distance 0 for this metric. And so, okay, they have to be equal to x. So the only thing in that open ball is x itself. Okay, so every singleton set, subset of x, is open. And well, we can take arbitrary unions of those as well. So in fact, every subset of x is open, and that is none other than the discrete topology on x.